Hi everyone, welcome to the next video. We're going to be talking about differentials and local linearity. Here are the objectives, and let's get started. So a function is said to be linear over an interval if the difference quotient turns out to be a constant. You remember that the difference quotient is f of x plus delta x minus f of x all over delta x. And so basically it's the slope, right? We're talking about the change in y over the change in x. So when that's a constant, that means that the function is linear. But if you had a curve, which you can see here on this diagram, if you have a curve, this is a quadratic function, and a tangent to that point, if I put this curve, if I graph this curve on a calculator and I just kept zooming in and zooming in and zooming in and zooming in here at the point of tangency, you would begin to see this right here, which is the graph of this function tends to become linear the closer and closer and closer it gets to that point of tangency. So that's what's being called locally linear. So if you zoom in enough times, if it's differentiable, which means if it's continuous and every point exists here, if you zoom in enough, you're going to be able to see that this turns into a straight line. So you can see here that you have the definition of a derivative, the limit definition of the derivative. And you can see that it's the limit as delta x approaches 0 of the difference quotient. So what we have here is, since delta x is very, very small, we can approximate the derivative by using this formula. All right, so what we want to do is we want to just kind of rearrange it a bit and say this, that if we approximate it, f prime of x is close to the difference quotient, the closer that we get into it. So we have f of x plus delta x. Notice that we're just taking off the limit. We're not doing an exact definition, we're doing more of an approximation. We're approximating. Okay, so if we rearrange this a bit, like for instance, we take, we multiply both sides by delta x, right? So delta x, f prime of x, is approximately this. And then we add that f of x to the other side, then we end up with f of x plus delta x, f prime of x, is equal to f of x plus delta x. All right, so the function of x plus a little bit is equal to the function of x plus a little bit, right, because this delta x is a very, very small amount, is equal to the function plus that little bit times the derivative. So here in words is what I said before. It says the value of the function at x plus a little bit equals the value of the function at x plus the product of the derivative of the function at x with the little bit, or multiplied by the little bit. And that's what that looks like. So we're going to use this formula to approximate the value of a function, and or we're going to use it to find the error of an approximation. So we're going to use differentials to approximate the square root of 9.01. Okay? So the first thing we want to do is we want to make some definitions. So we're going to say that x is equal to 9. The little bit, delta x, is going to be 0.01. And the function is going to be the square root of x, right? We're taking the square root of something plus a little bit. All right, so we write out, we know that f of x plus a little bit is equal to the function plus that little bit times the derivative. All right, so we have everything we need here. We just want to plug that in. So we have f of 9 plus a little bit equals f of x. F of x is the square root, right? So f of 9, f of x, plus 0.01 times the derivative of the function at 9. All right, so the derivative of the function is 1/2 x to the negative 1/2, which is 1 over 2 square root of x. Okay, so I put in here, here's the equal sign. What is f of 9? Well, that would be the square root of 9 plus 0.01 times the derivative, 1 over 2 times the square root of 9. Okay, so you end up, when you put that in your calculator, right, this is just 3, so 3 plus this little bit is going to be approximately 3.00166666. So this is just showing you how these relationships fit together. You would definitely do the square root of 9.01 on a calculator, but you can also see that you're getting the exact same differential by using this method as you would if you put that into the calculator, because it's very, very similar. It's just slightly larger. Okay, our next example, we're going to use the differential formula to use differentials to approximate 3.98 to the 4th power. So once again, let's define what we're trying to find here. So we know that f of x is going to be equal to something to the 4th power. Okay, and then so we know the derivative of that already. That's going to be 4x to the 3rd. Okay, and then we know that x is going to be 4, and our differential this time, we pick a value, and we want to pick it as close to 4 as we possibly can, because the further you get away, the higher the error. So the differential is going to be negative this time, and it's going to be 0.02. All right, so we know that f of x plus delta x is approximately f of x plus f prime of x times delta x. All right, so f of 4 minus 0.02 is equal to f of x. So this is going to be 4 to the 4th plus the derivative, 4 times 4 to the 3rd times negative 0.02. Okay, and when we put that in our calculator, we're going to get approximately 250.88 using this method. If we just put it in our calculator, you get 250.91827. That's pretty close. That's pretty darn close using a differential. So, so far we've talked about the different notation that we use in calculus. Y prime, f prime, dy dx all mean the first derivative. Now, differentials, we're going to take this dy dx as two different real numbers. So the change, the derivative with respect to y over the derivative with respect to x. So as they become, dy dx becomes a real number ratio, and also if f is differentiable at x, then this dy dx is equal to the derivative. So we would have this ratio is equal to the derivative, and you would have something like this. So dy is equal to the derivative of x times dx. So you may be asking yourself, why on earth are we doing that? Well, because this is an alternate formula. Remember that the change in y is really equal to this from the difference quotient. dy is the change in y, and dx is equal to delta x. So this is approximate. This is an approximate value. All right, so dy is going to be a dependent variable, and it depends on the values of x and dx. So be sure you have this written down as an alternate formula to the one that we did before. Okay, so let's use this alternate formula to estimate the change in area when the radius of a circle is increased from 3 to 3.04. Okay, so we have the area of a circle, which everyone remembers, pi r squared. If you take the derivative of that, that's 2 pi r. Okay, so we would have that the derivative dA, remember we have dA dr, the derivative with respect to r, is going to be approximately equal to the derivative of a. So if we rearrange, we end up with the derivative of a equals a prime dr. Okay, so the dr is the change, so that's going to be 0.04. R is going to be 3, right? And so we have dA equals 2 pi r dr. So if we put in the values for that, we have r is 3 and dr is 0.04, and this is 0.754. So if you change the 9 pi, if you compare the 9 pi to the 3.04 squared pi, it's a pretty good approximation. It's pretty good. It's close. Okay? One more. So we have the radius of a sphere is measured to be 4 centimeters with a error of plus or minus 0.01 centimeters. Use differentials to approximate the error in the surface area. Okay, so the surface area, the surface area of a sphere is 4 pi r squared. So ds, we'll just call it s, dr is going to be 8 pi r. So ds is going to equal 8 pi r dr, right? R is 4. Dr is plus or minus 0.01, right? So if we put that in there, pi r is 4, and this is plus or minus 0.01, and that's going to equal plus or minus 1.0053, and that would be the error. So you can see here that it's talking about the accuracy of the linearization, and so it should kind of make sense that the closer you are to the point of tangency, the less error you're going to have. The further away that you're moving from the point of tangency, you can see that it gets further and further away, and that's going to be where the error is. So here's an underestimate, here's an overestimate to it, because here's the point that you're finding, right? You're finding something along the derivative, you're using the derivative. And so that error is going to get more and more pronounced as the further you get away, the further that you get away from it. So I hope you took good notes. I have a feeling you're going to have some questions, and so be ready with those when we come to class next time. So take care, and we'll see you then.